So, let us recap the structure of premixed flames, which is very important. So, it is in the context of, say, for example, take a context of a flame propagating through the unburnt mixture here, and the burnt gases leave the other side. So, this is the flame. So, this unburnt reactant has a given equivalence ratio and temperature, and the flame propagates in this direction with a velocity of SL. So, now when I say structure, it is nothing but the profiles of temperature, mass fraction of reactants, etc. across the flame. So, in this graph you can see that we are trying to plot temperature, Y of reactants, heat release, etc. as a function of distance which is normal to the flame. So, the reaction zone which is shown here, this is the flame zone where all the reactions are taking place and the reactants are consumed. So, and this is the unburned side. For example, this is the unburned side, and this is the burned side. So, the reactants say have a temperature, initial temperature of T0 here, T0, and this continue to be T0 until a particular distance from the reaction zone, where due to conduction of the heat from the flame to this zone, which is called preheat zone, the temperature rises and reaches the temperature of Ti. So, the Ti is usually called ignition temperature, where the chemical reactions will kick in at a faster rate. Then in the reaction zone, the temperature further increases and reaches the value of the flame temperature Tf. So, coming from the unburned side to the reaction zone, the temperature increases in a zone called preheat zone due to the heat conduction from the reaction zone, and reaches the ignition temperature. Then further it increases to reach the Tf. Reactants, so which is nothing but fuel plus oxidizer in flammable proportions. The mass fraction remains intact. Then this decrease here is due to the diffusion of this towards the product side, basically where the products are formed here, and its concentration decreases. Now, in the reaction zone, its concentration decreases further due to its consumption, and within the reaction zone or flame zone, the reactants are fully consumed. Heat release rate, which starts just before the reaction zone, attains its maximum around the location where the reactants are consumed, and once the reactants are consumed, the heat release drops to 0. So, we have already seen. So, this type of drawing profiles of mass fraction of reactants, temperature, even also we can also plot a profile of the mass fraction of the products. So, this is called structure of a premixed flame. Basically, the interaction between the reaction zone and the preheat zone will actually lead to the propagation of the flame. See, for example, this flame has to go towards the right, consuming the unburnt reactants. Here, unburnt reactant. That means that this has to heat up the next layer and increase the temperature to ignition temperature and propagate in this direction. So, this is what is basically will happen as it propagates. If you sit on the flame, for example, then the unburnt reactant will be coming towards the flame at the same velocity of SL. This is the concept of the premixed flame propagation. So, what happens other than the temperature increase in the preheat zone, there are some high reactive species like H, O, OH, which are called radicals. They are also formed in the reaction zone. So, you have seen that initiation reactions will cause it. So, for example, CH4 plus M gives CH3 plus H plus M, something like this, or O2 plus M giving 2O plus M. So, you can see that the formation of HO, similarly O plus H plus M reacts to form OH plus M. So, these are the reactions which will produce highly reactive species called radicals in the reaction zone or in the boundary of reaction zone. Then they will be transported from the reaction zone to the preheat zone. So, that will also make the initiation reactions in the preheat zone very close to the reaction zone. Okay. So, heat transfer from the reaction zone to the preheat zone is one of the important things. Similarly, the radical transport from the reaction zone to the preheat zone also occurs. So, now this will cause the chain initiation reactions etc. in the slightly in the boundary of the preheat zone towards the reaction zone, and in the reaction zone the chain propagation and chain branching reactions will occur, producing more of these species radicals. Now, after the reaction zone, what happens is the in the reaction zone basically what happens, we have already seen that the mass fraction of the reactants reduce due to its consumption, and heat release is there. It will reach the maximum at the location where the reactants are consumed, and rise in temperature occurs from the ignition temperature to the flame temperature. Then when the reactants are consumed, the chain termination reactions kick over, so that the heat release will rapidly reduce. First it will increase to attain the maximum, then after the reactants are consumed, then it will reduce to 0 value. Now, after the reaction zone, the recombination zone, which is next to the reaction zone to the right, you will see that the recombination of species will occur. So, based upon, say for example, based upon temperature, CO2 will dissociate, CO plus O2 will form CO2, they will be in equilibrium and so on. Similarly, if the reactant mixture is rich enough, that is more fuel is there than the oxygen, then the fuel will come out of the reaction zone and burn in the recombination zone or the zone which is next to that, or only the hot gas passes through that. So, based upon the heat loss etc., the temperature will reduce in the recombination zone. So, rich mixture, the fuel will burn as a diffusion flame in the recombination zone. Then we also saw about flammability limits. So, in an isolated system where we do not allow for any mass transfer of fuel or oxidizer, we have a system in which there is a mixture of fuel and oxidizer already present in some proportions. Okay. So, some percentage of fuel is present in the oxidizer and it has some equivalence ratio. Now, you try to ignite it using a localized high temperature source. Sustained reaction takes place or not will decide whether the mixture is flammable. Okay. So, because we do not allow for any further addition of fuel or oxidizer, what happens is in the isolated system, when you ignite the mixture is flammable, then ignition will occur and sustained reaction will take place. That means we do not need any additional oxidizer or additional fuel to cause the ignition. So, such a mixture which will not need additional, so already there is some proportion of fuel and oxidizer. Now, without need of additional fuel or additional oxidizer, if the mixture can ignite, then such a mixture is called flammable mixture. The flammable mixture is basically some amount of mixture in which fuel and oxidizer are going to just react without any requirement of additional fuel or oxidizer. Okay. when you have too less of fuel, that is more of oxidizer, then it will not ignite. If you have too much of fuel and a less amount of oxidizer, then also it will not ignite. So, this will contribute to lower flammability limit and higher flammability limits. So, generally we say limits of flammability, and what are the factors affecting this? They are temperature, equivalence ratio, then pressure, etc. Okay, now there are standard test procedures which are available. So, let us have say a tube in which you have a mixture which is fed, and there is a ignition spark plug and the ignition source can be given here, so that a flame forms and propagates through a certain height. Then we say the mixture is ignitable. Similarly, I have a spherical vessel. At the center of this vessel, I ignite the mixture, whatever mixture I fed into this center, I ignite. And then if the flame forms and at least propagates to 90 degrees, then we say that the mixture is flammable. So, these are all standard test procedures, and when I do this, I will find that, so this is isolated system, I do not allow for any more fuel or oxidizer. Whatever be the mixture, it has certain amounts of fuel and oxidizer, and now I ignite it. When I ignite it, I get the flame which is initiated, and not only the flame should initiate, it should propagate to certain distance. In this case, that height, whatever be the height from the ignition source, it should propagate to a particular height. That means the flammability is confirmed. Similarly, in the spherical vessel, it should propagate to an angle, spherical angle of 90 degrees, then it is flammable. If it is not, then either more fuel or more oxidizer is required for the mixture to be flammable. So, that means that the limits of flammability are extremely important for premixed flame propagation. Some values of flammability limits are shown here for several fuels. Here, the lower limit corresponds to the minimum amount of fuel in volumetric percentage which is present in the mixture that will ignite. That means, when I say 5%, if methane 5% by volume is present in a mixture of methane and air, then this mixture will ignite. So, 95% by volume is air. So, that this will ignite. Similarly, if you increase the methane percentage to 15% of fuel in the, so 15% methane is present in the mixture of methane and air, then also it will ignite. So, you may wonder what is the stoichiometric fuel in the mixture, that is 9.47%. Okay, that means a mixture containing 9.47% of methane by volume in methane air mixture, then that is stoichiometric percentage. Now, lesser than this, it is lean mixture, and how lean I can go? From 9.47 I can go to 5% of fuel. Similarly, in the rich side, when I increase this to reach say more and more fuel, then I can go to 15% of fuel, that is it. Then this is a range. That means, if I have 4% of methane in the methane air mixture, it will not ignite. Similarly, 15.5% of methane is present, then it will not ignite. So, within the limit of 5% of fuel by volume in the mixture or 15% of methane volume in the methane air mixture, the mixture will ignite. Other than this, we will not be able to ignite it. So, this data is given for several fuels here along with this stoichiometric thing. So, now we can see that propane also, it is somewhat 4 is the stoichiometric, and you go from 2.3 to 9.5. So, sometimes the richer limit will be higher, lower limit will be closer to the stoichiometric, and so on. Now, you see some special limits. For example, here acetylene 2.5% in acetylene air mixture, acetylene 2.5% by volume in acetylene air mixture will ignite. Similarly, you increase this to 80%, then also it will ignite. So, that is because of the high reactivity here. Now, see the corresponding stoichiometric volume, it is 7.72, very close to the lower limit, but higher limit is much one order of magnitude higher. So, it's about 8% here stoichiometric, to 80% if you increase also it will burn. Hydrogen also behaves like this. Hydrogen in air, 4% by volume of hydrogen will ignite. Similarly, but you see that the stoichiometry is about 29.5. This score is not very close. That is, you go to very low lean limit, it will work. As compared to the acetylene, 7.72 to 2.5 only it may work. But here about 30%, you reduce it to 4%, it will work. That is, one magnitude I can decrease, and some 3 times I can increase to about 75%, it will work. So, these high flammability limit fuels are very dangerous to store, because if you have a leak, a small leak also, that mixture will ignite. Similarly, if you have a storage tank in which small amount of air goes in also, it will ignite. So, these are all the problems in handling high reactivity fuels. See, even carbon monoxide, for that sake, we can say it is highly reactive, CO, because you can see that 12.5 to 74.2. Now, this is only in air. Now, if you increase the concentration of oxygen, then the flammability will become more and more wider. Okay. For example, if you take pure oxygen, for hydrogen I can go from say 3% to about 95% by volume. So, that is the problem if you have pure oxygen environment. So, the reactivity will still increase, and you will see that you are going to go into higher or wider range of flammability limits. So, handling these fuels will be more and more complex. So, other saturated hydrocarbons, these alcohols, etc., are very easy to handle, but on the other hand, you will see that even benzene is okay, but you can see that these 3 fuels are highly reactive, so that the wide range of flammability is got. So, this idea should be with us in order to store it properly, leak proof storage, etc. And once the leak occurs, proper sensors have to be put to sense it, and immediately some diluents have to be injected, so that the flammable mixture will be diluted and it will not cause any ignition. Now, after measuring the flammability limit using standard test equipment, what we can do is we can correlate this. That is, what is the lower flammability limit? We can correlate using the heat of combustion itself. Okay. Suzuki and Koide have given these 2 correlations for lower flammability limit and upper flammability limit just by measuring this and correlating with the delta Hc, that is heat of combustion, standard heat of combustion or calorific value. So, calorific value is used to calculate this, and the simple expressions, nonlinear dependency of LFL and UFL are seen for the fuels, for several fuels. So, flammability limits are of practical interest for us, because they invoke the safety considerations, and this has to be taken into account when the fuel is handled properly, when they are stored or they are transported or they are supplied from one part of the process industry to another part, and so on. We will be very extremely careful. Okay. Now, in this, these correlations will be extremely useful, because every time we cannot do the experiment, and also once the correlations are done, then we can also use some mixing rules to find the low flammability and higher flammability for the mixtures of fuels. That also can be done. So, in these correlations, you will see that the heat of combustion delta Hc has a unit of kilojoule per mole, gram mole, and this LFL and UFL are nothing but the volume of fuel in air, just exactly like what we have tabulated here. volumetric percentage of fuel in the air mixture. That is what is given here. So, the flammability limits correlations are very much useful for us to design explosion vents and other things also. Okay, so very important parameters for us to understand when there is a premixed reactant mixture available. Now, as I told you, important parameter for a premixed flame is how fast the flame will consume the premixed reactant. In terms of velocity, it is called laminar flame speed. SL. Now, this laminar flame speed basically is the normal component of the unburnt reactants coming towards the flame and burns there. Now, to understand this, the parameters affecting SL, we can analyze this laminar flames using premixed flames using three types of theories. One is called thermal theory, then second one is the diffusion theory, and third is the comprehensive theory. As the name suggests, thermal theory assumes that the mixture is heated by conduction to a temperature at which the rate of reaction is sufficiently rapid and self-sustaining. That means the heat transfer from the flame to the unburnt portion. So, we have already seen this, there is a flame and the flame propagates in this direction. So, there is a neighboring zone just to the right of the flame which is heated by conduction, so that the temperature of this mixture which is present here is increased to a sufficient value which I call T ignition, such that the flame is established there, that is the flame just moves there. So, only heat transfer from the flame to the that is preheat zone or the unburned part will cause the flame to propagate. That is the theory behind the thermal theory. But diffusion theory is not at all going to consider the temperature increase. They say that it is because of the active species and radicals such as H, O and OH which are formed in the reaction zone that will allow that is actually formed in the reaction zone, but they actually diffuse towards the preheat zone or unburned. That will cause the initiation of the reactions in the next layer of the flame, such adjacent to the flame. That will cause the initiation of the reactions, allowing the flame to propagate in that particular direction. So, in the diffusion theory, diffusion of active species such as atoms H, O and radicals OH etc. from the reaction zone to the unburnt reactant mixture is assumed to initiate the reaction. Okay. So, thermal theory only heat, that is a premixed stuff. When you increase the temperature to a ignition temperature, it will ignite, that is it. But in the diffusion theory, the initiation step of chemical reaction mechanism where the fuel splits into lower order fuels plus radicals, that is very important. So, that is what is considered in the diffusion theory. But in reality, both occurs, that is the heat from the reaction zone to the preheat zone, the heat transport by conduction. Similarly, the diffusion of active radicals into the preheat zone from the reaction zone, both will contribute to the flame propagation. Now, this requires detailed analysis. So, we have to solve for species transport, energy transport etc. So, that means we need comprehensive models or theories to do this. So, these are the three theories which we use for analyzing the laminar flame propagation or in a premixed flame. So, in this we will go into the thermal theory and see what are the concepts used there. Thermal theory was actually introduced by Maillard and Leach-Chatelier, where they used the two-zone model. The two-zone model, which exactly is like a reaction zone and a preheat zone. There are two zones, one in the zone 1, which is the preheat zone. The reactant mixture is preheated to a certain temperature called the ignition temperature, like this. So, this is the reactant temperature, initial one, and this is the ignition temperature. In the zone 2, which is the next zone called reaction zone, reaction is complete and the temperature reaches the maximum value, TF. This is the exactly same thing which we have seen in the structure of the premixed flame, where there are two zones. Zone 1 where the reactants are preheated to ignition temperature, zone 2 reactions are complete and final temperature is reached, that is it. So, interface of the zone 2 and zone 1, the temperature reaches the ignition temperature, and in the zone 2 it reaches the flame temperature, TF. So, the preheat zone, here actually in the structure we have plotted non-linear variation of temperature. Again here in the zone 2 it is non-linear variation, but what we can assume here is the slope of the temperature profile in the zone 1, which is the preheat zone, can be assumed to be linear. Just say like this, linear increase from T0 to T1 or Ti, okay, linear. Then there is a certain thickness of the zone 2, which is the reaction zone, which is designated as delta. Okay. Now, let us see how the thermal theory is analyzed. So, here energy balance in terms of mass flow rate of reactants, its initial temperature, specific heat and thermal conductivity, and the flame thickness and its area is used basically. So, what happens is, for the mixture, so this is the reaction zone, preheat zone. In the zone 1, for the mixture to be heated from T0 to Ti, okay, the mixture is coming towards the, so this is the flame, reaction zone represents the flame of certain thickness delta, from which the reactions are complete, in which reactions are complete. So, towards this the unburned reactants come in at a certain flow rate, m dot. It has some specific heat at constant pressure, Cp, and what is the temperature rise? Ti to T0, so Ti minus T0. So, this m dot Cp into Ti minus T0 is nothing but the heat which is required to rise the temperature of the reactants or the unburned mixture from initial temperature of T0 to the ignition temperature Ti. This is heat required. How this heat comes in? That is due to the conduction from the reaction zone to the preheat zone. So, this lambda is the thermal conductivity. Thermal conductivity. So, this is dt by dx, gradient of temperature. So, within a short distance of del, the temperature rises from Tf to from Ti. Ti to Tf, the temperature increases. So, the temperature change divided by the distance, that is the gradient of temperature, Tf minus Ti divided by del. So, this is the this. So, into area of cross section, what will be the area of cross section? That is A. So, the heat required for the reactant mixture to increase its temperature from T0 to Ti is m Cp delta T, m dot Cp delta T. So, this is kg per second and this is joule per kg Kelvin and this is Kelvin. Okay. So, you can see this is watts. Similarly, here thermal conductivity, that is watt per meter Kelvin, and this gradient is Kelvin per meter and area is meter square. This will also will give the unit of watt. So, this is the balance, energy balance. Now, let us see what is mass flow rate of the reactant. If rho is the density of the reactant, A is the cross section area where the reactants are flowing in a pipe, for example, and U is the velocity. So, now perpendicular to the flame, what will be the velocity? That will be the flame speed, laminar flame speed SL. So, I can say the mass flow rate of the unburnt reactants will be equal to rho. So, I can say rho U also, rho of the unburnt reactant into area of cross section into the laminar flame speed, which is the normal component of the velocity towards the flame. So, that is m. So, now m is known and this equation is known. From this, try to write SL, because now if you put m as rho A SL, I can find an expression for SL here like this. SL is nothing but lambda thermal conductivity divided by rho Cp, lambda by rho Cp, which is what? Alpha into 1 by del into Tf minus Ta divided by Ti minus T0. So, this is the expression for the laminar flame speed by thermal theory, where a simple heat balance of what is the heat required and what is the heat conducted from the reaction zone to the preheat zone. These two are balanced and we got the expression. So, alpha 1 by del Tf minus Ti divided by Ti minus T0. Okay. So, this is the expression for SL.